In this lecture, we will discuss the communication protocols.
When talking to someone on the phone, there is an accepted set of procedures that should be followed. For example, when you answer the phone, you usually start with the word hello, and then you wait for someone to respond, and you just keep talking to each other until one of you says bye. So we need something similar to computer networks. If we're going to have meaningful communications, we need a set of procedures that specifies how the exchanges will take place. And this network etiquette is achieved by the means of network protocols. Well, what's a protocol? Well, in networking, a protocol is a mutually agreed upon set of rules, conventions, and agreements for the efficient and orderly exchange of information. Now, even though the internet has hundreds of millions of machines and they're made by tons of different types of manufacturers and they're located in so many different countries, they can all exchange messages correctly and efficiently for one reason. They all agreed to use the same protocols to govern that exchange. Now, you might think that something as large and vast as the internet would be managed by governments or major industries or an international agency, but that's not really the case. In fact, the internet is operated by the Internet Society, which is a non-profit, non-governmental professional society that's composed of more than 100 worldwide organizations in 180 countries that's united by the common goal of maintaining the viability and the health of the internet. So we have this group along with its subcommittees, which consists of groups like the Internet Architecture Board and the Internet Engineering Task Force. And with all these groups together, they establish and enforce network protocol standards. Now, the protocols that govern the operation of the internet are set up as a multi-layered hierarchy, where each layer addresses one aspect of the communication. And they're structured in this way because of how volatile the telecommunications and networking are. So if we divide the protocols into separate independent layers, a change to the operation of one layer will not necessarily cause a change to the other layers. And this makes the maintenance of the internet a lot easier. The internet protocol hierarchy, also called a protocol stack, has 5 layers. This hierarchy is also referred to as TCP/IP after the names of 2 of its most important protocols. So we have 5 layers here. So we have the physical layer, we have the data link layer, the network layer, the transport layer, and the application layer. And we're going to discuss all 5 layers in more detail. We'll start by discussing the physical layer. The physical layer protocols govern the exchange of binary digits or bits across a physical communication channel, such as a fiber optic cable, copper wire, or wireless radio channel. Now, these protocols specify such things as how do we know when a bit is present on the line, how much time the bit will remain on the line, whether the bit is in the form of a digital or an analog signal, what physical quantities are used to represent a binary 0 and a binary 1, and the shape of the connector between the computer and the transmission line. So the goal of the physical layer is to create this bit pipe between two computers, such that the bits that are put into the pipe at one end can be read and understood by the computer located at the other end. So once we've selected the physical layer protocol, and we can do this by purchasing a modem, getting a digital subscriber line, or even using a mobile phone with wireless data capabilities, we can transmit binary signals across a physical channel. And from this point on in the protocol stack, we don't need to worry about engineering issues such as voltage levels or wavelengths or even radio frequencies. Those details are hidden inside the physical layer, which takes care of all the necessary bit transmission services. So from this point, all we need to worry about, or all we need to know about the communication channel is that when we ask the physical layer to send a bit, it's going to send that bit. We'll next discuss the data link layer. Remember that the physical layer protocols create a bit pipe between two machines connected by a communication link. However, This link is not an error-free channel because of different types of interferences or weather issues or any other factors. We could have some problems when we're transferring the data. One such problem is that the bits that come out might not be an exact copy of the bits that went in. This creates what we call an error detection and correction problem. So how do we detect when errors occur, and if we do get an error, how do we correct it? Also, because we want to receive complete messages and not raw streams of bits, we need to know which bits in the incoming stream belong together. So we need to know the start and the end of a message. And this is called the framing problem. So it's the job of the data link protocols to address and solve these two different issues. And the way we do this is we actually do it in two different stages. We can kind of think of them as sublayers. So we have what's called the medium access control, and then we have the logical link control. So together, these two services form the data link layer. So remember we talked about how local area networks communicate by having several machines connected to this single line where all the communication is shared within this line. But remember there's a small problem with this where we can only send and receive one message at a time. If we try to send several things simultaneously, the messages get jumbled up and it just doesn't really work for us. So that means we need to be able to determine how to allocate this shared line among the competing machines before we actually send something. And that's where the medium access control protocol comes into play. It will actually determine how to decide ownership of the shared communication line whenever we have multiple nodes that want to send messages at the same time. Now, this could be done in a centralized manner. So we would create a single master control node that's responsible for deciding who gets ownership of the line at any point in time. Now, it's pretty easy to do, but it's really not used. It's very rarely used. One reason is because it can be pretty slow determining who gets the ownership, because each node would send a request to the master, who then has to decide which node gets the line, and then must inform all the other nodes of the decision. And this takes quite a bit of time, so it makes the network highly inefficient. Another problem with this centralized approach is it's not fault tolerant. So if the master node fails, well, the network is in big trouble. That would just be really bad. So what most medium access control protocols do, including Ethernet, will use what's called a contention-based approach. And here, there's no central authority, and all the nodes will equally compete for ownership of the line. So whenever a node wants to send a message, it first listens to the line. It checks to see whether or not the line is currently being used. And if the line is idle, if it's not being used, then the node will transmit its message right away. But if the line is busy, then the node's going to wait. It's going to wait a little bit. It's going to wait for the status, and then as soon as it becomes idle, it transmits. So they're basically taking turns is what's happening. So you listen to the line to see if it's being used. If it's being used, it's just going to wait until the line is cleared, and then it will send its message. Otherwise, it'll just send the message right away. Now, there's still a problem here, because let's say we have two more users wanting to send a message while the line is in use. So both of them are monitoring the status. They're waiting for the line to be cleared. And then let's say they both find out at the same time that the line is idle. So they decide right at that exact same moment that they're both going to transmit the message. Well, this is what we call a collision. And it's a very common occurrence in contention-based networks, just like in Ethernet. So when this collision occurs, all the information is lost because now you have two messages being sent at the same time. So they're getting jumbled up. So according to the Ethernet protocols, whenever we do get a collision, the nodes will immediately stop sending. So it'll just say, okay, stop what you're doing, don't send anymore, just stop what you're doing, you're making matters worse. And then both nodes are going to wait a random amount of time, and then they'll attempt to resend. And the idea behind this is it's very unlikely that both nodes will select the exact same random time to try sending the message again. So it's most likely that one of them will be able to send it, and the other one will probably have to wait until the other node is done first. But we just basically have them stop and then randomly pick a time to try again. Now let's suppose our network uses a different type of connection. Let's say it uses the point-to-point links instead of the shared line approach. So what this means is that we don't need the medium access protocol controls anymore because any two machines along the path are connected by a dedicated line. So it doesn't matter which approach we're using because now we have a sender and a receiver who want to exchange a single message. And then these two nodes are directly connected by a channel. So it's the job of the logical link control protocols to solve the error detection and correction problem and ensure that the message traveling across this channel from the source to destination does arrive correctly. So it is in charge of making sure that it has the correct sender and the receiver. So we don't need to mess with any shared lines because all the nodes are all connected together. Now, how is it possible to do this? I mean, we're not going to be able to eliminate errors, but we can at least detect that an error has occurred and then retransmit a new and unblemished copy of the original message. So we use what's called the ARQ algorithm, which stands for Automatic Repeat Request, and this is the basis for all data link control protocols in current use. So let's suppose we have two nodes, A and B, and A wants to send a message to B. So A is going to add some additional information to form a packet. So it's going to add a sequence number that will uniquely identify this packet. So it could be like 1, 2, 3, or so forth. But if you have a set of packets, it pretty much creates an order for the packets, and so each packet has a unique identification number. It also adds some error checking bits to the packet, so that way B can determine if the packet was corrupted during the transmission. It also will add a start of packet, or SOP, and an end of packet, which is also known as an EOP, delimiter to allow B to determine exactly where the packet begins and where the packet ends. So the packet would then be sent across the communication channel bit by bit using the physical layer protocols that we've already talked about. So when B receives the packet, it'll examine the error check field to make sure that the packet was transmitted correctly. Now, what makes the ARQ algorithm work is that node A maintains a copy of the packet after it's sent. So if B receives the packet correctly, it'll return to a special acknowledgement message or abbreviated ACK that contains the sequence number of the correctly received packet. So now node A will know that this packet was correctly received and can discard its local copy. Now, if B does not correctly receive the packet, or if the packet was completely lost, that can happen, then A will not receive the ACK message from B, and then after waiting a while, A will resend the message to B using the copy that was stored in its memory.